5.4, number 73. So they give us a graph of a function and they ask us to do some stuff. First, estimate the zeros of this function here, which I wrote right here. So it's the net area function starting at 0. All right. So the integral from 0 to x of your function. But what is a 0? A 0 is a value of x that makes the function equal to 0. So I take my integral and set equal to 0. So what is it really saying? It's asking, when is the net area equal to 0? Because that's net area. Well, I have the first easy one. I claim at 0, the net area is 0. Because what's the area under the curve from 0 to 0? 0, because there is no area. So my first answer I claim is 0. But then check this out. As I integrate from here to here, that answer is going to be the area under that curve. So I'm going to color that in with a nice greenish color. Ooh, that's kind of hard to see. Let me do a dark green. Yeah, that's better. So as I integrate from 0 to 4, it's going to be the area of that triangular-ish shaped thing right there. Now, how do I get back to 0? I need to subtract the same amount, right? So I have to subtract what? I think I have to subtract all of this. So when will my net area be 0? Well, when I integrate from here and I move across, now I'm up to that area, and it's not going to become 0 until I subtract all that. So at 10, my net area be 0, because that will cancel that out. So I claim those are my two critical points, which I think it looks like it to me. All right, or not critical points, sorry, take that back. Those are my two zeros. So when t is 0 and t is 10, my area function, that will be equal to 0. Now we want to estimate local maximums and local minimums. So here's the next great question. A local max or local min is where the derivative changed from positive to negative, you have a local max. If the derivative changed from negative to positive, you have a local min. So therefore, let's find the derivative. So what's the derivative of this guy right there? Well, you had a theorem. If you have a constant and an x, the derivative, you just plug x into the function. So this becomes f of x. So that is our derivative. So this here actually is the derivative of a. And if it is, what happens right here at 5? The derivative changes from positive to the left, negative to the right. Therefore, I claim there's probably a relative max at 5. So I'm going to say a rel max at x equals 5. So that's my part B. Part C, sketch a graph of A without a scale on the y-axis. So this is just guessing. You are guessing, and I will show my guess. Okay, here's how it works. This function here is net area. So as I move farther right, I just add more area. So at the beginning, I add that slice. Let me change the color to red. So I add that area to my function. So at first it's going to start at 0. And then I add that much area, it's going to go up. But as I move to the right, do you notice that slice I'm adding less because it's a smaller area? And then here I add even less because it's a small area. And here I add even less. So my area is going to increase, but as I move towards like 5, it's gonna add very little here because it's a very thin slice. So the function at first is gonna go up, but then it's gonna slow down at that point. So at first I add lots of area, but then it's gonna slow down. It flattens out because I'm adding less and less. I'm adding smaller and smaller pieces, so the graph doesn't increase anymore, it kind of flattens. And then when I get here, I'm subtracting a little itty bitty piece. Then I subtract a bigger piece. I subtract a bigger piece. I subtract a bigger piece. So as I move right, at first it starts to decrease slowly, but the farther I go right, it starts subtracting bigger and bigger pieces, and then it's going to drop back down to 0 at that point. So that's the graph. I know it's hard to wrap your head around that. If you didn't see it right now, I just advise that you rewatch this video when I post it and try to, in your brain, fit the pieces together and have that make sense to you.